All right. Thank you very much, Adi, for your kind introduction. It's my great pleasure to be here, and thank you for inviting me to give this presentation. So what I'm going to talk about today is about the application of resistive memories in the domain of FPGA. So we're going to go towards like an application, a very unconventional application of resistive RAMs, but without having any like really disruptive computing paradigm compared to in-memory computing. So for this work, the general idea is that resistive RAMs are for us a low-power FPGA enabler, and by low power, I mean it's actually near VT FPGA enabler. And all the work I'm going to present right now, which will be more in terms of circuit and architecture, can be generalized to many different memory technologies. So I'm going to talk, of course, about resistive RAMs in particular, because that's something that we control very well in fabrication, but it can be done with different switching mechanisms and so on and so forth. Resistive RAMs emerging memory technologies are interesting because they are back-end offline compatible, so you can stack them on top of CMOS and really explore the integration of the two. However, what is even more interesting is that they do have great device properties. Of course, everybody is talking about flash replacement, you know, like large density, low power, low write power, and so on and so forth. But it also has a very interesting thing is that you can engineer more or less all the properties of these devices. Properties being, you know, set and reset voltages, being the resistance windows depending on the energy as Johannes presented. So you have really a lot of freedom to make some great trade-off with such kind of devices. So what we're going to look at right now is, can we do something beyond the use of pure memories? So we're not going to simply replace the SRAM memories of FPGAs by RRAMs, but we're going to see how we can put them into the routing structures of FPGAs and reduce the power consumption by 5x while still providing some benefit in terms of area delay product. So when we talk about FPGAs, we need to consider where to play. So FPGAs are reconfigurable logic systems composed of basic logic elements and ultimately lookup tables that perform the combinational operations. And these elements are immersed in a complex array of routing structures. And these routing structures are actually composed of routing multiplexer programmed by SRAMs. So if we start looking at the area, delay, and power breakdown of such an architecture, you can see that only 14% of the area is used for logic computation. And one can draw very similar conclusions for delay and power. So by essence, FPGAs, even though they're extremely useful for many applications, are very inefficient architectures. You do pay a lot of price for the programmability and reconfigurability. So our goal is to improve all these different metrics, area, delay, and power, and we'll do that by playing on the routing costs. So our goal is to improve the current bottleneck of FPGAs, which is routing, and in particular, the routing multiplexers. So FPGAs do rely heavily on routing multiplexers, and here's a typical structure of such a circuit element. So they're typically composed of multi-stage multiplexer, usually two-level for performance, multi-stage multiplexers for control signal reduction. And every single stage is composed of MUX tree with transmission gates. So, you know, like NMOS and PMOS devices in parallel to propagate the signal. So the general idea here is to replace these transmission gates by resistive RAMs. Resistive RAMs are two-terminal resistive switches, so you can switch them between two stable resistive states. So it's actually like a switch, and it does behave very similarly to a transmission gate controlled by an SRAM. So what we propose is to make a one-to-one replacement of the transmission gate by resistive RAMs, and that way you'll be able to achieve the same functionality than a regular routing multiplexer by creating a connective path, programming connective path within your memories. So what are the interests of such structure? First of all, you get a non-volatile routing multiplexer, so non-volatility is a given in this case. But most interestingly, you get a performance improvement, because it's possible to program resistive RAMs to achieve very low on-resistance state, much below what you'll get with the current on-channel resistance of a MOSFET. So you'll basically decrease the RC delay of your routing multiplexer, and in turn get performance benefit. And what we'll see in some next slide is also you get power benefits, because it does scale very well with the power supply reduction. All right, so that looks all great on paper, but let's try to go beyond this very naive view that simply replace like transmission gate by the RRAM. We need to understand how to program this structure, what will be, how can I manage the large voltages required for programming, how can I isolate these different structures, and so on and so forth. So I'm going to continue with more circuit level work, and in particular, the first thing that we got interested in is the programming structures. How can I efficiently program resistive memories in such kind of organization that will be in the data path of my logic? So one general statement with resistive RAM is that, hey, if you want to minimize the impact of programming structure, let's just use the minimum number of transistors, right? So I'm going to go with the 1T1R structure, and that will be a done deal. But actually, it's not always the best. What is very important is to consider what is the current density that you can achieve with these structures. And it's definitely not a given. So if you look at this 2T1R structure that one can use to program the memory set and reset, so invert the polarities, if you start drawing the Kirchhoff diagrams and so on and so forth, you'll see that the transistor is never saturated. You'll always end up in a situation where some transistors do work in the linear region, so you do lose a lot of programming density, of current density, sorry. So what we do propose is to use 4T1R structures. You'll always have a great path between VDD and ground, and as a result, you'll be able to achieve a much higher current density for a given sizing of your device. So in this particular case, more than 2x compared to existing structure reported in literature. So the general idea and the general message here is that with a 4D1R device in the application of RRAM-based FPGA, we do have more transistors, but in fact we have less area, which is what counts at the end of the day. So based on this general idea, 4D1R structures are good to achieve low on resistance in our resistive RAM. So now we try to get a better understanding on how to make an optimized routing multiplexer. And here's the general message I would like to give here. Physical design does play a big role. It's very important to consider how to arrange your different wells and the different types of transistor you're going to use to program these devices. And here's our solution. So we basically split our two wells in between the two parts of the multiplexer, and we do not try to simply isolate the programming structure on a separate well. Because if we try to simply isolate our programming structures, we will lose a lot of area, many jumps between the different parts of the circuits. And on top of that, splitting our wells in such a way will give us some very interesting advantage that I'm going to just present now. So here's a typical operation of our 41R MUX. So on this structure, you have on the left part a simple tri-state inverter used for isolation. On the right part of the circuit, you do get an output inverter, and in between, you get your RRAM-based routing. If you want to operate that, just assume the memories were programmed, and you're going to route signals in between the different part of your, like from one input to the output, and simply using all the signal railing between VDD and ground. If you want to program this device, you're going to try to apply a potential difference across your resistive RAM. And here's an interesting thing we can achieve with our multi-well structure. is that by simply lowering the potential on the depend well, so on the right part, we will be able to actually double the potential drop we'll see across our resistive RAM with regard to the nominal voltage of our transistors. So what is interesting here is that we'll be able to program a memory with a vprog equal to twice the nominal voltage of our transistors without risking any breakdown for this technology. So this is quite interesting here because we don't need to use like I/O transistors to program the RRAMs, and that gets very interesting for logic, when we use both RRAM and regular transistor in the same architecture, we don't pay too much price in simply programming this structure. So in this particular case, we do have our RRAM programming voltage that is larger than the nominal voltage of our transistor, again, without any risk for the device. If we want to reset, that's the very same idea, but instead of shifting down the right part of the circuit, we do shift up the left part. And again, we'll be in the same condition, this time for reset, but without risking any distraction. And that that was discussed in our recent TCAS1 paper, where we also really studied all the implications for implementing that on bulk or FinFET or whatever, in particular with all the latch-up diodes and so on and so forth. So you basically do get still a limit. vprog should be lower or equal than 2 times VDD, but still you can locally boost your programming voltage. Regarding our multiplexers, we did perform some real physical design estimations, and we implemented that with the ASU 7 nanometer FinFET PDK. And what I'd like to compare here is, this is an SRAM-based multiplexer, and I'm comparing that to the RRAM-based multiplexer. What is quite interesting here is that since you're non-volatile, you do not have, well, you do store the memory locally, and you don't have to use anymore the fairly big SRAMs that you had before. So even though we have all the programming circuit that we need, to account for, they are actually in the same range than what you used before with some SRAM circuits. So you do get an area benefit for creating a RRAM-based routing multiplexer. But what is actually extremely interesting with such structure, and so far I just talked about that's area, that's performance, but what about power? And I'm going to make here a very important point for this technology. If we start looking at one of the major problems of CMOS, that's what was discussed earlier in many different talks. CMOS does behave very badly when we start reducing VDD. Because of the non-steep slope behavior and so on and so forth. So you basically lose a lot of performance when you reduce VDD, even though you keep having good benefit in terms of power. What is interesting with our RRAM-based multiplexers is that they do not degrade as fast as a CMOS-based multiplexer in the presence of a power supply reduction. So on this plot, you see the energy on the right and delay on the left evolution for CMOS and RRAM-based routing multiplexers, so SRAM in blue and RRAM in red, for a different set of VDDs. And what we can see is that while the energy does reduce for both technologies significantly, quadratically actually, when you reduce VDD, we are able to maintain the same level of performance for much longer, and in particular, we can play in the near VT and sub-VT range without any performance degradation, but still getting the power benefit. So that's one of the key messages here. RRAM-based routing multiplexers can operate at low voltage without delay degradation. And that gets very interesting, because if we now start to study that for our 7 nanometer routing MUX, and here I'm showing that the delay, and on the other plot here I'm going to show the power for a regular CMOS at the 7 nanometer and RRAM-based FPGA multiplexer, sorry, for different voltages. What we can see is that at nominal voltage, we do get the performance benefit I told you at the beginning. So 1.7x improvement in delay, 2x improvement in power. But more importantly, when we start going into the near VT domain, we do get a 5.8x improvement in power delay product. So the general idea is that RRAM-based routing MUX are good to operate in the near VT regime. And we wanted to push that further and see what we were getting at the architecture level. So, but to do that, we had to build a very custom tool to study that. So in the FPGA world, there is this architecture exploration tools like VPR, where we can, study different trade-offs for your architecture. But these tools are really made for CMOS. So we created an extension called FPGA Spice that actually dumps an entire FPGA architecture in Spice netlists. And we're able to simulate that in a Spice simulator. So of course, we had to play with some tricks to speed up the simulation. But the general idea that I want to bring here is that the numbers I'm going to report are based on electrical simulation and compact models. So and here's what we're going to get is that for a resistive RAM, so here I'm basically showing area, delay, power, ADP, PDP for classical SRAM-based FPGAs and RRAM-based FPGA at nominal and near VT and sub-VT. And what we can see is that our MUX level benefit translates directly to architectural benefits with a 40% improvement in ADP and 5x improvement in PDP, which is quite significant without changing any computing paradigm, and there is a one-to-one correspondence between actual architecture and this one. So, but can we do something beyond that, beyond this very simple one-to-one correspondence, and can we explore domain-specific optimizations? And it's very possible to do that. So if we look at programming transistors, again, we talked about 41R structures. This is a big deal. Programming structures are a big deal for RRAM-based FPGAs. But we can do things more interesting. In particular, if we look at our structure, RRAMs do need individual access. So we need many transistors in the structure. And they need large current, fairly large current. That's why 41Rs were good. And so we have many large programming transistors that are merged into the data path. So possibly, they could lead to some performance degradation, and we need to study that carefully. We should not oversize our transistor and just get what we need. And here's an interesting effect of resistive RAMs. These novel devices are bringing specific challenges. That's one of them. But they have new opportunities that can help mitigate that. And with resistive RAM, what is very interesting is that their delay of a RRAM-MUX, which is actually linked to the on-resistance of the memory device, will depend on the programming energy and the programming current that you use, and as a result, on the size of your programming transistors. So we can really try to study what is the exact on-resistance I need in the different part of my FPGA. So there are some new circuit sizing opportunities, and we looked into that. So that's a modeling of our routing MUX. So we did with a closed form expression, playing with the Elmore delay. I'll go quick with the math, that can get very ugly. But the general idea is that if we start taking the delay of our multiplexer and inject the fact that the on-resistance depends on the size of the programming transistor, we can get to an optimum. So every programming transistor in the FPGA can be sized to the optimum in order to achieve what? What you see on this plot. If you have a very small programming transistor, you get a fairly large on-resistance, and as a result, the RC delay will be large in your circuit. On the opposite side, if you have a very big programming transistor, you'll get a very low on-resistance, but you do pay the price of a large parasitic capacitance. So you'll also start degrading your performance. So you need to shoot right on the sweet spot, and this sweet spot depends on the different circuit sizes that circuits that you have in your circuit, and you should not have a uniform distribution. So what is very interesting here is that we are using a resistive memory device, but the performance and the parameters of this memory will depend on the sizing of your circuit, and as a result, you will not have a uniform memory technology all over your chip. So same physical technology, but different usage and different parameters. Another interesting result about these RRAM-based routing multiplexers is that they do scale much better than CMOS transistors, CMOS multiplexers. On this plot, I'm showing the delay for RRAM-based and CMOS-based routing multiplexers as a function of the number of inputs. And what we can see is that RRAMs do scale much better because we have a lower parasitic capacitance at the internal node. And what is quite interesting here is that we'll have an opportunity to use larger multiplexer in our structure and revamp the FPGA architecture a little bit. So we have the opportunity to use larger and faster multiplexer in the FPGA architecture. And that was explored as well to create, local routing that merge the access from the global routing and the local multiplexer as well, and also getting some larger switch box capacity. So I'm not getting into much details here, but I'll be happy to talk about that in more detail if you want. And the general idea is that the architecture itself can be improved beyond what I said. Right before concluding, I'd like to show you a brief summary of the requirements in terms of memory technology that we need. What is very interesting is that this is typically what you have with a flash memory requirement, right? So you want to have very large endurance, very large frequency, many writes in your memory, and you can, of course, play a little bit with your resistance ratio. If you are sensitive enough, you're good with that. What is interesting here is that this specific requirement would lead to wrong, estimation for an FPGA. Such a technology won't be efficient to create a RRAM-based FPGA. But this technology, it's actually just the way you use an existing technology, resistive RAMs. You program them and you use them with the level of energy that you need to target a specific application, standalone memories. If you start using them outside of this range, you can actually play, within this spot where you'll basically get a much larger resistance window, but pay the price of a lower endurance. You're really unlocking, some interesting application for RRAM-based FPGAs, and that's what you would need in this particular case to get. Just want to emphasize again that I'm not talking about a different memory technology. It's just the way it is programmed and the way it's used. So you can really trade off frequency and endurance. So now let me conclude with a few takeaway messages. And we all agree that emerging technologies do bring new opportunities. And in particular, here we saw some unconventional use of memories. And of course, process design co-integration is fruitful for emerging technologies. It's not only a matter of devices. It's a matter of application, a matter of circuit design. What can we do with them, and how can we co-integrate everything? And I believe that there are some interesting opportunities for high-performance, low-power FPGAs around the corner. And finally, I'd like to acknowledge so the funding agencies, my former boss, Nadine Micheli, who worked very closely on this topic, and all the students who got involved over the few last years. Thank you very much for your attention, and if you have any questions, I'll be pleased to answer.